Go on, close your eyes for just a second. Now imagine trying to get around the room you're in. It's tough, right? We rely so much on our eyes. But what if I told you there's a way to see with sound? To map out a space, find something, or measure a distance, all without any light. Sounds like something out of a comic book, but it's very real technology.
To really get how we pulled this off, we've got to look to nature's original expert. I mean, think about it. How does a bat fly through a pitch black cave or snatch a tiny bug out of the night sky with, perfect accuracy? The answer is just so cool. And the answer is echolocation. It's basically a natural sonar system. A bat sends out these super high-frequency sound waves. When those waves hit something, say a moth, they bounce back as an echo. The bat's ears are so incredibly sensitive that they pick up that echo and build a 3D map of its world using just sound. It's an absolutely amazing system.
And, this is something we humans are really good at. We see a brilliant idea in nature and we think, hey, I bet we can build that. We've created technology that lets our machines see the world in pretty much the exact same way. So let's dive into how it all works.
All right, so let's get to the heart of it. How exactly did we take this amazing natural ability and shrink it down into a piece of tech you can hold in your hand?
Well, we call it an ultrasonic sensor. The key word there is ultrasonic, and all that means is that the sound waves it uses are at a frequency way, way higher than 20 kilohertz, totally outside the range of human hearing. So even though this little gadget is basically shouting and listening, to us, it's completely silent.
And here's a super common one you might see around, the HCSRO4. You'll notice right away it looks like it has two little eyes. Well, one of them is the transmitter. You can think of that as the mouth that sends out the sound pulse. And the other one is the receiver. That's the ear, just waiting to hear the echo come back.
Okay, so how does this whole shouting and listening thing actually turn into a super precise measurement? It's all based on a beautifully simple idea called the pulse echo principle. The process is actually pretty straightforward. The transmitter sends out a little blip of sound. That sound travels through the air till it hits something. Then it bounces off that object, and the echo travels back to the receiver. It's just like shouting into a canyon and hearing your voice come back, right? Except this is all happening way faster and at a pitch we can't even begin to hear. So really, we can break this down into a simple three-step dance. First, it transmits a pulse of sound. Second, that sound wave reflects off an object. And third, the receiver just waits to receive that echo. Transmit, reflect, receive. It's a nice, simple cycle. This comparison really makes it all click, doesn't it? The bat's mouth, that's our transmitter. The bat's ears, that's our receiver. And the bat's brain, which is doing all the complex processing to figure out where its next meal is, well, that's just like the little computer chip doing the math for the sensor. It's a perfect example of biomimicry, engineering inspired by the genius of nature. Okay, so the sensor knows how long it took for the echo to get back. But time isn't distance, so how does it convert that little tick of a stopwatch into a precise measurement in meters or centimeters? It uses this pretty simple formula. See, we know the speed of sound in the air. It's more or less constant, about 343 meters per second. The sensor measures the time it takes for the echo to return, so we multiply them together. But, and this is the crucial part, why do we divide by 2? Well, think about it. The time the sensor measures is for the sound's round trip, all the way out to the object and all the way back. We only want the one-way distance, so we just cut that time in half. Simple as that. Let's put some real numbers to this. Imagine the sensor measures the echo's travel time as 10 milliseconds. That's just 1/100th of a second. We plug that number into our formula, multiply it by the speed of sound, divide by 2, and boom, we get a distance of about 1.72 meters. This is literally what's happening inside your car's parking sensor when it starts beeping at you. Now, for any of you who are into the nitty-gritty electronics, here's a quick peek under the hood. A little computer sends a tiny electrical trigger pulse, which basically tells the sensor, go. The sensor then sends out its burst of sound. At that exact same moment, another electrical signal, the echo signal, starts. Think of it like hitting start on a stopwatch. When the sound comes back and hits the receiver, you hit stop. The duration of that echo signal is the exact time we need for our distance calculation. So we've gone from bats in a cave all the way down to the electronic signals. But where does this technology actually pop up in our world? I mean, what's the big deal? Let's check out some of the real-world uses. You see, the real power of these ultrasonic sensors is just how incredibly reliable they are. Unlike a camera, it doesn't care if it's pitch black or broad daylight. It's not affected by color. It can even see a perfectly clear glass wall that a camera might miss entirely. This makes them amazing for tough environments. Think of dusty factories or foggy weather. It's this toughness that's made them a go-to tool in robotics, automation, and of course, in all our cars for things like parking help and even self-driving systems.
So, from a bat hunting for its dinner in the dark to a car that safely parks itself, we've seen how a simple principle from nature can be engineered into some seriously powerful technology. We've basically given our machines a brand new sense, the ability to see with sound. It really makes you wonder, right? What other hidden senses are just waiting out there for us to figure out and harness? And as this tech gets better and better, where are we going to point these new eyes next?